Stuart? Well, welcome back, everybody. How was Monday and Wednesday? Piece of cake? Any big questions looming? We spent a couple minutes recapping just to make sure we understood everything from J-Young sequence. I also have those lectures, or at least versions of them, posted online from last year, the year before that. They're all about the same, but you never know. Sometimes I say tidbits that are more important than others. We will be coming back to this problem, mixture models, so I wanted to bury something in to this class that they don't cover a lot of in the book, but you can come up with really interesting distributions by mixing distributions together. So, just real quickly, J-Young told you all about this stuff, right? Let me ask a question. So we're IID sampling from this. How do we sample from this additive mixture model? And it's additive because I'm adding together weighted distributions. The weights here live between 0 and 1. So there are elements between 0 and 1 with the property that the sum of the weights, pi k, equals to 1. I'm just going to sum over all cap k of these components. So this is a finite mixture model. The finite bit is that there's a finite number of components. You might infer from that there's infinite mixture models that exist. So we're probably not going to say too much about that, but I might maybe towards the end of the class, if we're so inclined. So you might say, if I were trying to infer from something like this and I knew the basic structure, how would I learn k? So that might be an inference problem. If you knew k, problem's easier. And I'm going to have you study problems where you, and this is into chapter 7, some algorithmic problems, where I'm going to give you k, and I'm going to say you get to know it in this problem. But let's say you didn't know k. What you could do is fit it under different k's, different cap k's, and then compare those fits to each other. There's lots of different ways that you could compare the fits. So you could look at likelihoods or something like that. So you would want to be a little bit careful because you would have more parameters for more k, and you can't just make a direct comparison between those two things. So you'd probably need to compare the likelihood and then penalize them somehow. So if you had more parameters in a model, it would probably fit better. And so you wouldn't want to all of a sudden make it fit perfectly. And the reason why is because if you try to forecast out of a perfectly fitting model, it doesn't account for any uncertainties. They overfit. So there's ways that you could do this. If you're a Bayesian, you could put a prior on k. So you could put a parametric prior on k. Let me just ask a question, since we're just still kind of thinking about all these things we have to talk about in this class, and there's a whole bunch of them. What kind of prior might you put on k? So a prior is a distribution over k. So just throw one out. Some distribution on k. What at least would be a sensible distribution on k? Cap k. Let me ask a different question. Would a normal distribution be a good choice? Why not? That's right. Can't take negative values. That's a good reason. So there's other constraints as well. K is an integer. So what distributions do you know over integers? Plus. So that would probably be the immediate one people might jump towards. There's negative binomial distributions. We'll play around with those. Negative binomials are mixture models of Poissons in some sense. So I'll say something about that later on in this class. It's a different type of mixture. But you can take distributions and somehow combine them together and get other distributions out of them. These are what I call modeler's tools. So this is very important. So I can almost come up with any like smooth shape out of this. And the name of the game is to figure out what is k in all of it. Jared, I'm kind of curious. What distribution would you throw on k?
Maybe a geometric.
A geometric. Okay, so you've got it like truncated somehow. So would be another possibility. So he might say, I'm going to automatically truncate this thing. So in some sense, There's something called the Dirichlet process. I was wondering if you've heard of that before. And that's kind of a modern, in vogue way to do it. We will not cover that in this class, but there's lots of stuff to learn about. Okay, real quickly, if I knew what K was, and I knew what these model parameters were, and I knew what that distribution was right there, how would I sample these xi's? So what I mean is that I'm going to reach into this distribution, it looks like this. These heights of these components, so this would be a component, have something to do with how much weight we're putting on them. So that's consuming that much of the area of everything. Of course, there's some overlap in here. These things are superimposed on each other. How would I sample from this distribution? To sample. From star. That thing. There's basically 2 steps to it. First step, Josiah.
This is what Jay described. You can use a uniform 0, 1, and you can choose, and then based on your uniform 0, 1, you're going to choose which distribution you sample from. So if you have half the weight on one particular distribution, then if your uniform falls between 0 and 0.5, you're going to sample from that distribution.
Yes. That's an inverse CDF sampler for sampling from a particular distribution. So that's an implementation that certainly will work. There's another way you could express that. Probably saying it less procedurally, but just saying something mathematically. So I'm going to sample from some random variable. I'm going to call it a multinomial. So I'm going to take a k-sided coin and I'm going to flip it. And I'm going to see which side it lands on. The sides of the coins are going to have probabilities pi k on them. That's called a multinomial distribution. So you're thinking of a k-sided coin and flipping it with those probability weights. Josiah gave us an algo from actually sampling from it, and it kind of makes sense. So that's actually the inverse CDF sampler implementation, or I would say it's probably something you might even just intuitively come up with. So, but I'm going to say you're going to take K, I, and I'm going to take it from a multinomial. And the probabilities in this multinomial are going to be pi 1 up to pi k. So these are the problems. This should be cap k. So k-sided coin flip. And you could think of different ways to transform a uniform into that. So if I sampled a uniform and it was less than pi 1, I would sample from component 1. If I sampled a uniform 0, 1 and it was bigger than pi 1, but not bigger than the addition of pi 1 and pi 2, then I would sample component 2. So you're just sampling from the cumulative distribution. And you're effectively inverting that somehow. So this is the component number, I sample that. And then once I know which component I'm going to sample from, then I sample from that distribution, that continuous distribution. So I take the xi's, and I take them from its distribution. These distributions are allowed to change. I say distribution, I mean density in this case. They're allowed to change, but I think Jay Young's example was they were all normal distributions. But you could mix together different distributions. In fact, it's incredibly common to sample from a distribution and then have a point mass with some weight at 0 or something like that. So if you're sampling Poissons, sometimes we see more zeros than we would expect out of a Poisson, and so we put in this mixture component and it's a point mass at 0. And we could think of that as a distribution as well. And they have weights on them. So we just sample the xi, iip out of that distribution. In Jay Young's example, he just changed what the model parameters were. This was a normal, for a normal additive mixture model. He was just taking that to be x, and it had some mean attached to it, and it had some variance attached to it. And I think that in the example, they just picked 1 to be the variance. I say they, I mean me. So I coded that thing up years ago. So just to make it simple, we could change the variances as well. So that's how you sample out of those. Each time you just sample the component, then sample from the distribution. So pretty easy to do, very flexible. Here's a theorem for you for any smooth distribution. Smooth, you know, continuous. So I can take a normal mixture model and approximate that distribution. So you can come up with stuff with long, heavy tails, skewed stuff, multimodal stuff, and you could model it using normal distributions. That's kind of a nice thing that you could do. It's not different from like Fourier's theorem or all of these theorems where you're taking some basis and you're combining them in some superimposed way to come up with another function. Lots of different ways you can do it. Okay, so we know what a mixture model is. We'll come back around to this and I'll have you infer from mixture models in this class. Probably a little bit more than the book intends, but I want to give you some tools that you can take into your future. There's lots of different ways that you can infer from a model like that. I'll teach you the EM algorithm, and then if you're so inclined to take my Bayes class, I'll show you how to do it with MCMC, Markov Chain Monte Carlo. We will just barely be touching on that in this class. Okay. So this was just kind of a freebie. Some complicated distribution where we wouldn't know what the answers are. So if I gave you something where it's just a one component distribution and I asked you to infer something, you might be able to do it mathematically. So this was just designed so that you're thinking, I don't know, I've got some multimodal distribution, I'm trying to infer a statistic, I don't know what the asymptotic distribution of that statistic is. And I don't know how quickly the asymptotics kick in. So this was just motivation for maybe doing some bootstrapping. So the idea here is that you're going to get some number of data points from this distribution. Something like that. And then what you get to see is some histogram approximation of all this. So you don't actually get to see the function, but you get to see your data points. And you could build in some histogram, and depending on how big n was, would tell us how close that histogram approximation is to the actual curve. So the name of the game in statistics is you get to see the data, you don't get to see all the model parameters or all of what's going on inside of the model, and so you want to infer what that is. A statistician always wants to quantify their uncertainty about things. So let's say you wanted to come up with a test statistic. I'll just point out, we'll do a review session also on Wednesday at 5:30 in this room. So I'll be here, and I'll hang out for as long as you guys want me to, answering questions about homework, theorems in the book, scanning ahead, where we're going, so on and so forth. So open-ended. So the idea is that you get to see some collection of data, X, and so far I've said everything is IID in this example. So you get to observe this. And somebody wants to compute some statistic. And Jay Young probably gave you a couple, so I asked him to walk you through the mean and the variance. So let's just use the variance, for instance. So maybe our test statistic, T of X, so test stat, is maybe some of the xi's minus x bar squared, where x bar is the sum of the xi's divided by n. And what do you guys normally divide by? To come up with an approximation of variance. So I'm going to say this thing is approximately equal to sigma squared, the variance. And the variance, just to be specific, is the expectation of the x's minus the expectation of x squared. So that's what it is, and we can approximate it by changing our expectation signs into some empirical averages. What do you guys normally divide by?
Minus 1.
You guys feel strongly about that? So let me just ask the question, why do you normally divide by n minus 1?
unbiased.
It's unbiased. So it gives you this property right here. So this thing, a lot of times people call it S squared, the sample variance, and the expectation of S squared is equal to sigma squared. So that's the unbiased estimator that has this form in it. So does anybody ever divide by anything else? You guys always divide by n minus 1 every single time? Your teachers told you to do that, right? Anybody ever divide by n? It's not called S squared anymore when you do that. It has, I don't know what you would call it. So call it something else. Turns out this one is on average closer to the truth than n minus 1. It's biased, but it has less variability. So we see that trade-off. In fact, this isn't even the optimal one of this form. So if you want to scan ahead in chapter 7, there's a problem in there that tells you there's even a better estimator than that. So it's kind of funny. We oftentimes in practice use the wrong thing for juvenile reasons. I mean, that's a reason. But what I would want is something that's close on average, closer, that accounts for the variability as well. So anyway, we can divide by n minus 1. My real answer to this is, if this matters, then you have all kinds of problems. So, obviously n would be really tiny if it made any real difference to you. So sometimes we're just kind of quibbling. There's a theoretically slightly better answer, but we're going to want to know about that kind of stuff in this class. Okay, we'll stick with the unbiased one. Hopefully I'll convince you later on, biasness is the only criterion to look at. There's other things you want to account for. So if we wanted to compute this from our data set, we would get exactly one number. And so I don't know what number this is because I don't know what those numbers are right there. But we get entirely just one number. And the statistician always wants to express their uncertainty in things. So that's what the bootstrap really tells you about, is it tells you about this uncertainty. So what you might want to do is go back out into the population, collect another data set of size n, and compute that number again. And you would get repeat the process over and over again, and eventually you'd get a full distribution of that. So if you repeated this process, you'd get one number. If you kept on repeating it, you would be able to draw like what the distribution of that number is if you repeat it. Now, in statistics, we can't do that. I can't tell somebody, just go back out there and get more and more samples. And the real reason is because if I were able to repeat this, let's say cap r times, I would have a data set of size r times n, which would have a lot less uncertainty attributed to it. And so I'd probably want a better estimator and not just want to quantify all my uncertainty on everything. So the bootstrap helps to address this. And it says instead of going back out into the population over and over again, you go back out into your sample, this sample, and if this sample is representative of the true distribution, then something very similar to going back out into the population and resampling n samples again is to go back out into your original sample and just resample from it n times with replacement. And so you're going to basically come up with some quantification of the uncertainty in that estimator. So the bootstrap will not give you a better estimator. On average, if you averaged all your bootstrap replicates, you would get back to that number that you would have. So if you took an average of all of your bootstrap replicates, then you're going to get your original estimator back. It'll converge to that. But you will get this distribution from bootstrap replicating. So basically the answer here is you get an uncertainty I'll say quantification. People seem to like this. I used to get really upset when I'd see everybody in other departments talk about uncertainty quantifications. So I'm just going to hijack the word right back from you and go, what we really mean is stats. We want to do probability. So we want to understand things on a probabilistic scale, which is quantifying our uncertainties about everything. So the distribution that you get from your bootstrap replicates and your original distribution aren't exactly the same because you're getting repeats of things and you're always confined to your original data set and you can't see numbers outside of it. So it's close, but it's not exactly the same. So it can be a nice tool. So just real quickly, what are some of the limitations of bootstrapping? This is an In-Young Kim question. So if any of you are taking her class and preparing for a qualifying exam, she always almost asks a question that can be answered with bootstrap. So she's almost looking for it. So, and she'll probably ask you something like, what are the limitations? So what are some of the limitations of bootstrapping? No limitations. It's a nice tool, use it all the time. Brendan?
If your sample from your population isn't actually representative.
Yeah, that's true. If that were true though, if that were really true, if it wasn't a very representative sample, you probably can't answer anything with the sample. So it needs to be at least somewhat representative. But there are some test statistics that you can't really understand the uncertainty with. So if I wanted to, instead of looking at like something like this nice continuous quantity, if I were looking at like the max order statistic, then the max order statistic is the maximum of that set. And if I just resampled from it, the max order statistic would never get bigger. It would always be pulled to the left. And so you'd be entirely biased. So there's some statistics that you can't infer well and quantify the uncertainty with the bootstrap. So things on the boundary. So I would say boundaries are problematic. So estimates of the boundary are problematic because your sample only has like one piece of information about it. Also, it requires that you're doing IID sampling in the first place. So if everything was dependent on each other, you couldn't do this. This required IID-ness. So remember, I'm going back out into my original data set and I'm resampling from it in a simple random sampling fashion, i.e. the IID bit. So I'm IID sampling from that, which is mimicking IID sampling from that. So if these were dependent samples, you probably couldn't do this. So for like time series or spatial analysis, that might be problematic. Saying that, there are incarnations of the bootstrap that try to address this. There's block bootstrapping where you kind of break some of the connections every once in a while, but you sample things in batches. There are things called the parametric bootstrap where you employ some parametric estimators and you bootstrap over those. That can be helpful. So there are other forms of bootstraps that try to address some of these questions, but we're not going to go into all that right now. Okay, so I think we all understand a little bit about why the bootstrap works. Any questions about this? Let's just look at it real quick. Oh, let me just ask one more question. How many bootstrap replicates are there? I'd asked Jay Young if he was interested in recording so I could watch it myself, but I don't know. He didn't want to be put on the spot, so I'm not sure exactly what he covered. So, quick question. How many unique bootstrap replicates are there? We're dealing with a sample of size n.
2n minus 1.
2n minus 1, she said. And Jay Young did a good job of going through the combinatorics on this. So I usually hear things like 2 to the n, where it's like the in or out sort of thing, but they're not accounting for all of the different partition groups. So if you draw the right picture with the stars and bars sort of analysis, where you've got your number of elements and then you've got your partitions, you can come up with this. So if you have any questions about that, review session would be a good time, and I can go back through that. Okay, this number is huge. So one common question might be, why not enumerate all the Bootstrap replicates out there and just enumerate all of those and create its distribution? And the real answer to this is it's just too big of a number. So, I don't know, did Jay Young compute this number for you on any data sets? Let's just look at it real quickly. It's bigger than you think. Bootstrap can work pretty good for relatively small samples. Of course, I need to define what relative is, but maybe 12 samples. So I plugged into this n choose k 12 times 2 minus 1, choose 12. So when n is 12, this number is 1,352,078. So it's massive. So there's a lot of them. So we usually do the thing that most statisticians do, and we just throw darts. So let's just do stats on this and just grab these uniformly. So randomly. So I'll just randomly sample them and crank this number up. And so how many Bootstrap replicates should we do? You don't need to enumerate all of them. What you really want to do is you just want to look at your test statistic, and anything that you're going to compute off of it. Let's say I want the variability of that test statistic. What I need to do is run the Bootstrap, compute that number, and then do it again and crank that Bootstrap replicate up. And if the number is changing, you don't have enough samples. Bootstrap replicates, I should say. So basically, you do the thing that engineering do. So just crank it up higher and higher and higher until that number converges. So anything that you want to report to whatever decimal place, make sure that you've run the sampler long enough so that that number is stabilized. So if you ever walk into a seminar and you're reporting numbers down to like 7 decimal places, I'm going to call you out on that. Because I'm going to know you have no precision in estimating that 7th decimal place. And so if you do report numbers, make sure that you can back those up. So if your estimates are only good to 2 decimal places, don't use Excel's default of like 82 decimal places and report that, because it just looks kind of silly. Okay, so you run it until it's big enough. So this first part is what Josiah was telling us, is it's the inverse CDF sampler from sampling from this multinomial distribution. Embedded in all of these are 3 different normal samplers. Randn is a normal sampler, and it's just shifting things over to +10, -10, +3. So the effective means are these 3 different means, +10, -10, and +3. And the mixture weights are these numbers right here. So this code is online, so you can look at that. You would never go back out into the population R times and resample over and over again, because you would be not efficient with the data that you're using. So this is just done for demonstration purposes so we can compare the Bootstrap to it. We're going to bootstrap some number of times. This number is going to be different probably from cap R. We want that thing to stabilize. We're using a computer, and we're not too concerned about the computer's effort. Computer doesn't have feelings, so we can make this thing bigger if we want to, and I can throw in extra zeros in here. If you go and you say, I did 1,000 Bootstrap replicates to In-Young Kim, she is going to call you out for it. She's going to say, not enough. So, and it's pretty comical when you see seminars and she calls somebody out, and then they go, well, I was trying to run my simulation study last night. So we get prepared for everything. So. Okay. So the rest of the code is just Bootstrap replicating. So the Bootstrap is this very basic algorithm where you're just sampling with replacement. I have been asked why not sample without replacement. And if you sample without replacement, you recover the original data set every single time. You get no uncertainty. Another question might be why you resample n times, because the test statistics that we're computing and comparing to each other, we want comparable. So as we change n, we usually change the properties of our statistic. So we want everything with the exact same property. So Bootstrap's relatively easy, at least this very vanilla version of it. And everything else here is just plotting. I assume Jae-Young showed you what a QQ plot was, but we'll look at one in a second and make sure that we understand that too. So I'll be asking you periodically to plot QQ plots. It's one of my 2 favorite plots. I use them all the time. So Bootstrap. This is just going back out into the population over and over and over again. I think there's about 50 samples here. So pretty good idea of what those 3 modes are. From the very last sample, this is how the code works. It ends up Bootstrap replicating, and it did it a bunch of times. And I always look at histograms and I think, I can't tell if they're the same or if they're different. I know that they're different. The question is are they about the same? So how close are these really? And nobody in the world that I've ever met can look at histograms and tell whether or not they're the same. So you know that they're a little bit different. That bar's a little bit higher, that one's a little bit lower. So Jae-Young, hopefully he isn't the first person that showed this to you. But if he is, congratulations, it's a good plot. What does the QQ stand for? Quantile. So what we're going to do is we're going to compare theoretical quantiles to empirical quantiles. So what you can do, this is generally how it's explained, is if I knew some distribution, let's say I knew something was normally distributed, or if I thought it was normally distributed, I could end up looking at the quantiles. So I could look at maybe where's 5% of the area, and I could end up looking at that 5% quantile. I'll call it Q of 5. And I could end up looking at a histogram approximation of something, and I could look at the empirical quantiles, and let's say there were 100 data points over here. I would look at where is the 5th biggest thing. So the 5th order statistic, that would be the 5% mark for 100 samples. So I'd end up looking at my empirical quantile at 0.5. And I would do that for a whole bunch of different biddings. I might look at Q10, and then I might look at EQ10 over here, and do it so on and so forth. The way that I'm kind of structuring this is I might chop this up into 20 bins and do this. You can do it for more than 20 bins. So you could do it for every data point in your empirical set. And that's usually what the computer will plot for you. And it's just going to plot these numbers next to each other. So it's going to take your theoretical and compare them to your empiricals. Empirical just means the things you've seen, the stuff you've observed. And they're going to plot them next to each other. And if they're a straight line, then they're at least equivalent up to a shift and a rescale. So if it's a line that's running through 0, the intercept is 0, and the line has a slope of 1, then they're the exact same and they haven't been linearly shifted. So I never really look at that. I just look to see if the line is about straight. Now, you don't have to do it with a theoretical distribution. In an empirical distribution, you can compare 2 empirical distributions to each other. And that's what we've done here, is we've done the exact same thing. So if you ask for a QQ plot and you just add it, hand it one data set, it'll usually compare to a normal distribution for you, a normal 0, 1. You can, of course, concoct any distribution for comparison. And that's what this code does. So the Bootstrap distribution and the replicated distribution from the population look about the same. And the obvious thing happens, they're a little off in the tails because the Bootstrap can't sample in the tails very often, and there's less data there. So that's what Brendan's talking about, is that we might not have great representation in the tails. So the Bootstrap also kind of doesn't tell you about the tails perfectly, and that might be cause for a lot of criticism. So the tails are extraordinarily important. So if you thought things were Cauchy distributed and you were doing Bootstrap and you only had like one outlying point right there, you might trick yourself into the uncertainty of everything. Okay, let's just run it one more time. If I turn down the sample a lot, let's make this like 9 or something like that, that might not be representative enough, and I wouldn't get a very good inference. If I were doing this in practice, I'd be playing around with B and cranking up B a whole bunch of times and making sure whatever I was reporting out of that distribution, it converged. So n is equal to 9, pretty small sample, lots of little weird things happen. So not quite straight. But I would say surprisingly decent. For 9 sample points out of a 3-component mixture model, surprisingly decent. So not great, but better than I would have thought it would be. Any other questions about bootstrapping? Okay. I'm going to have you guys code this up in a couple weeks' time. I'll have a project for you. What I'm going to have you do is I'm going to have you compare an analysis using the Bootstrap to a Bayesian method to an asymptotic method. So I'm going to have you compare it to the delta method, which is an asymptotic device. So 3 kind of conceptually very different things that are about doing the same thing, and there's different pros and cons to each one of them. So you'll get some practice with this. Okay. If you can do math, you should do it. So you won't have to incur all the computational cost, and you'll have precise answers. If you can't do all of your math and you need a quick answer real quick or something like that, things like Bootstrap are your friends. So we already kind of said something about xn, the max order statistic, wouldn't be something you would be able to treat using a Bootstrap. And so we probably need to learn the math for stuff like that. Let's just go back to where we left off last week on Friday with one-dimensional order statistics, and just make sure we understand this in general, and then we'll scale up to joint order statistics. So from last time, this is just a little bit more general. So let's say I want to understand what the distribution of the jth order statistic is. So the dist of xj, where I have some sample of n data points. So this is going to be the jth largest. And I have an original data set, x1 to xn. So in this, we get to know what n is. And I'm going to presume that we know what the model is. So this is kind of the big fiction in my class, is I always get to know what the model is. So there's this extra step when you go to apply everything, is you're going to be looking at things like QQ plots to make sure that your modeling assumptions are appropriate. So I'm going to say each xi is going to come from some density. I'll end up writing down what the random variable is there. X, I'll use this X right here. So I probably should bold that X. Sometimes I cap it, but I don't want it to look like that one, because they're different X's. So this is just denoting the space where the random variable lives in. This is an instance of the random variable, and this is just a dummy argument. So a lot of things look the same. I goes from 1 to n. Everything is IID in this analysis. If you're trying to understand order statistics and things are not IID, the formulas would be arbitrarily complicated. So everything I'm showing you pertains to the IID case. And the cumulative distribution is just the integral of f of x dx. So that's the cumulative. And if we can write down both of these things, you could write down the distribution for the J order statistic. So this is about what we did last time. If I wanted to know what fxj was, so this is the cumulative distribution for the jth order statistic. So different random variable. There's a bunch of different scenarios that I need to enumerate through. So basically, I can have scenario 1, where I've got x here. And basically what we're asking when we write this thing down is this is the probability that our jth largest thing is less than or equal to x. So I've got that x right here, so one possibility for this is that I have j things over here. And I have n minus j things over here. So that's one possibility for all of this. I've got another possibility where I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So this is meant to illustrate j plus 1 things to the left of x. And then I would have n minus j plus 1 things over here. So n minus j minus 1 things would be over here. So this situation has the jth largest thing right here. So this is meant to enumerate the jth largest. This would be the jth largest here. This is the j plus first largest over here. But in both these scenarios, we have j things to the left of x. And I can do this all the way down to when I have n things less than x. And 0 things over here. So all those situations are situations in when the jth largest thing is less than x. If I ended up having the jth largest thing greater than x, that would not be a situation in which the jth largest thing is less than x. So what do I do for all of these cases? They're all different cases. And so I compute the probability for each one of them, and I sum them up. And that's how you would come up with the cumulative distribution for the jth largest thing. And so the question is how many different ways can I come up with a picture like this? I don't really care which order this came in, and I don't care how I exchange all these orders. So I need to account for all the different possible ways that we can do that. And for this one scenario right over here, there's n, choose j different ways that I can come up with a picture like that. Each one of those has probability attributed to it of f of x, where this is the original distribution. This is raised to the j power. I'll do it like this, j, and then the probability of all of these things being greater than x is the complementary probability. N minus j. And I can do something similar all the way down here. So this is going to be n j plus 1 f of x to the j plus 1 1 minus f of x to the n minus j, and I'll write it out like that, minus 1. So I've removed my brace from that. And then when I come all the way down here, I've got n choose n to the f of x, x to the nth power. And I've got 1 minus f, x raised to the 0th power. And I just sum up all of those different possibilities. And that's the cumulative probability of the J-order statistic. So we did that really slow last problem, with an actual concrete example. And so f xj of x is equal to the sum, where this is going to go, I'll call this I, goes from j, so this is the order statistic number, up to n choose I, f of x, to the I, 1 minus f of x, to the n minus I. So that's how you come up with that cumulative. I have a hard time remembering these things unless I can think about a picture. So if it's just a formula to you, you're going to forget it real quickly. So make sure you understand where these formulas come from. And if you don't understand, let's talk about it. So if I wanted the density for this, I would just take the derivative of this thing with respect to x. So that's my dummy argument that's in here. And this would be our density function. And I showed you another way to think about this. When we went in and we took this derivative, this reduced to just one term. There's a whole bunch of terms in here you would have to take derivatives over. And it turns out all of them cancel each other except for one. There's a bunch of negative signs that get thrown around. And so there's an easier way to think about this. If I asked you for the density explicitly, you might go through that calculation and come up with a cumulative. But you might think of just writing down the order statistics density directly. So here's an illustration. So I'm going to think about this x being right here. Now the density is measuring the instantaneous rate of achieving that thing at this point. So this is going to indicate the j largest thing at this point, right here. So there's one data point there. The way we expressed this before was there's this little skinny window, and we were going to call this a probability and then drive this window down until we got to its density function. And that happens with that instantaneous rate there. For this to be the j largest thing, we need j minus 1 things over here. And the question is how many different ways can I rearrange them? J minus 1 factorial, different ways. Each one of them occurs with probability f of x, where this is our original cumulative. And everything over here, this is going to be n minus j things. It can happen with lots of different orders. How many different ways can I loop these around and change everything? N minus j factorial. Each one of these happens with this probability. From this picture, I can construct the density just by producting everything together. So this is going to look like this. N factorial is the number of ways that I can permute everything. I want to take out the orderings that I don't care about, j minus 1 factorial. I've got these ones as well. N minus j factorial. You might notice that these don't add up to n. Where's the other thing? It's right there. There's no ways that I can rearrange it. So I don't write down the 1 factorial. This is going to look like 1. multiplied by the cumulative probability. This stuff here, how many of those things are there? This is j minus 1 times our density function times 1 minus fx to the n minus j. And that is that density function. So this is that. So if you go through all of this work and take a derivative over that big sum, you will always come up with this. Let me draw one more picture, and we'll do this slowly next time. But I just want to show you this. This will take 2 minutes. Let's do this with 2 order stats. We'll come back on Monday, and we'll pick up with this, and then we're going to pick up with transformations of order stats as well. So joint order stats. So let's just look at xi, the ith largest thing, and let's see how it's jointly related to xj, the jth largest thing, and I'm going to impose some ordering on that. So let's just draw a picture of this. I'm going to give this some different notation. Before I had an x that I attributed to the order statistic. Now I have 2 order statistics, so I can't use x. So I'm going to use something else. I'm going to use what the book used. So I'm going to call it u and v. Just need to be a little bit careful when I talk about this distribution. So this is going to be the ith largest thing. That's where xi is, ith largest. This is going to be the jth largest. And here's the hard part of the question. How many things are over here? Give you a hint. It's I minus 1 things. There's I minus 1 factorial ways of permuting it all. They all occur with this probability. Oops. Fx of u. So because we call that u right there. Let's just do this other one. This is going to be 1 minus fx of v over here. How many different things are here? If that's the jth largest, n minus j. What's the probability of being in this interval? It's the cumulative up to here minus the cumulative up to here. So this is going to be f of x v minus f x u. So that's going to be that probability of being in this interval. Right here, cumulative all the way up to here, subtracting off of that stuff. How many different things are in here? Say it again.
J minus I minus 1.
J minus I minus 1. That is correct. Very good. How many different ways can I rearrange that? That many different ways. So we'll come back next time. We'll product all these things up. And so we'll remember what the density function is right here. It's going to be fx u. And the density function right here is going to be fx v. We'll do something similar where we just product that all together. You could do this for any arbitrary number of order statistics and be able to write down that density function. If you wanted a cumulative distribution, you would go back the other direction and integrate over it. The reason we can't do the other thing is it's not clear what the cumulative distribution over a joint order statistic is, or a joint distribution. It's not clear how to add things together, in which direction. So usually it's a little bit easier to write down what the density function is, and then integrate over the regions that you specify. We'll come back next time, and then we're going to jump into that joint distribution of the range and the mid-range, In the book, there's this triangular picture, and we're going to be going through that picture. What I'd like you to do over the weekend is just look at the bounds on that picture and see if you can derive that triangular shape for everything. We'll pick up there after we write this down, and then we'll do that transformation, and we'll study that distribution. It's a good example. That's it for now, you guys. Have a great weekend. Anybody going to the game tomorrow?
Thank you.
VT could use the support. I'll say it that way. They got UVA.